In this tutorial, you will learn how to drive and dim LED strips using a 12-bit timer and lookup table. In the description below the video, you will find a link to a GitHub repository that includes a wiring schematic, the bill of materials, and detailed explanations for each line of code. So let's have a look at a bit of theory regarding how LEDs are driven, dimming, flicker, and pulse width modulation. Unlike resistors, capacitors or inductors, LEDs are nonlinear electronic devices. A small change in voltage results in an exponential change in current. That's why LEDs must be driven at their rated voltage and current, and the current must remain constant at all times. Unlike cob LEDs that are driven with a constant current, LED strips are driven with a constant voltage, because the required constant current is regulated on a per-string basis, either with resistors or driver ICs. In other words, an LED strip is nothing but a long string of parallel wired short strings. With only 3 LEDs per string, 12-volt LED strips are not very efficient. Nearly a third of input energy is wasted as heat at each resistor. 24-volt LED strips are the better solution, because with 6 or 7 LEDs per resistor or driver IC, much less energy is wasted. It may sound a bit confusing at first, but linear dimming appears nonlinear, while nonlinear dimming appears linear. In other words, because of human brightness perception, we have to dim nonlinear, so the change in illumination appears linear. Simple LED drivers generate perceptible flicker, even if we don't seem to notice it. And flicker is also visible at certain shutter speeds and frame rates when using a camera. Human-centric lighting should reduce flicker to a minimum. To dim LEDs, we use pulse width modulation, which means rapidly switching the LED on and off with an oscillating square wave to control the mean voltage. The dimming level is controlled by the mean voltage, and so we change the duty cycle per period. For visually correct dimming and flicker reduction, we need to apply pulse width modulation in a specific way. The higher we raise the frequency, the number of pulses per second, the perceptible flicker is reduced. Human brightness perception follows a curve described by the negative quadrant of a cube root function. We can use this function to generate pulse width modulation values so that the voltage change is nonlinear, but the brightness perception change is linear. Linear dimming with 8-bit pulse width modulation values appears nonlinear. Therefore, we'll use values on the cube root curve, and instead of complex floating point runtime calculations, we store and retrieve precomputed values from a lookup table. The benefit of using 12-bit resolution is that it provides us with 4096 values instead of only 255 with a standard 8 bits. The larger range allows us to distribute the pulse width modulation values much better. To keep it simple, we keep hardware to a minimum, because the clever stuff happens as always in the code. Here's an overview of all parts in case you're not so familiar with them. You'll need the specified components, but you can find cheaper substitutes online. The wiring of the setup is really straightforward. And now a quick demonstration. As expected, slow automatic dimming looks linear and smooth, thanks to the timer and lookup table-based approach to pulse width modulation. It doesn't matter how the dimming is triggered, automatically with a potentiometer, a momentary or proximity switch. Like I mentioned in the beginning, the clever stuff happens always in the code. Every line of code is carefully commented so you can learn the logic step by step. So please head over to GitHub and take a good look. Once you understood the approach taken here, you can confidently code dimming features for your own Lumina designs. And now it is your turn. Thank you for watching and listening.